Welcome back to Mechanics of Machinery. So today we will see how to draw displacement diagram for the followers. This is a general example I am taking for showing you the methodology to draw displacement diagram of all type of follower motions, because once you get the displacement diagram for the follower motion, it is easy to trace the required lengths to draw the cam profile. So first of all, you should know how to draw the displacement diagram for the different type of follower motions. Actually, we have learned it. There are basically four follower motions you should be able to understand, and you should be able to draw the displacement diagram: uniform velocity, uniform acceleration and return motion, UARM, or simple harmonic motion, which we call SHM, and the last one is cycloidal motion. So this is a general example I am taking. So your question may have additional data also for drawing cam profile and also finding velocity and acceleration values. But for drawing displacement diagram, this much data is enough. So this data I am taking as a general data for drawing and explaining all the type of follower motion displacement diagram. So let's analyze the question or the data given. So cam rises the follower for a 120 degree of rotation. So it is what ROTA, okay, rotation by a period of dwell for 60 degree. Then the follower descends the next 120 degree of rotation and again followed by a dwell period. So the follower is having a maximum lift of 30 mm. So in this we need this data, that is 120, that is for rising, that means outstroke. So I'm just writing outstroke is equal to 120 degree, and then we need this data that is followed by a period of dwell 60 degree. So first dwell is 60 degrees, then descends next 120 degree. So return stroke is next 120 degree and again followed by a dwell period, and the follower is having a maximum lift of 34. So maximum lift is equal to 30 mm. So if you analyze this data, just to draw a rough diagram or rough what you call a rough understanding of the data, that means your follower is having a maximum lift of 30 mm. So that means vertically it is having 30 mm, then it is having 120 outstroke, 60 dwell, then again 120 outstroke, and the remaining portion of the rotation as dwell. So if you draw a diagram based on that, you should get a rectangle like this, and you should have a outstroke section, that one, dwell section, return section or return stroke, then last will be the dwell again. So this is how your data should be looking like, and the last section you can calculate from. So last dwell section you can calculate easily, because total rotation is 360 degrees, so that will be 360 minus 120 plus 120 plus 60, that will be 240, 300, and last one will be 60 again. So this one will again will be 60 degree, because total is 360 degree rotation. They will not give you that or last dwell period. If they mention it just as dwell period, you can calculate by adding the other angles and subtracting it from 360, which is the total angle of rotation of. And this is 30 mm, that is lift. And you should get a cam profile with this as the outstroke, this as the downstroke, and last a dwell. So this is a rough idea of how to draw the cam profile. For each of the follower motions, this profile can be drawn differently. So let's see. So just to make you analyze, this is outstroke, dwell, return stroke, and again a dwell. So this is the basic diagram. Now let's draw the each case. First one we will deal with is the most easiest one, that is uniform velocity motion when the follower is having a uniform velocity motion. So we will use the same set of data for every case to explain. So first we have 360 degree in the horizontal direction. So you should scale it accordingly. So according to the length of the paper, you can scale it as much as you can. You can scale as well as 1 degree is equal to 1 mm, or you can take 2 degrees is equal to 1 mm. So if you take 1 degree is equal to 1 mm, so let's write that horizontal scale, or you can write x-axis scale. If you take it as 1 degree is equal to 1 mm, you will need 36 centimeter or 360 mm for horizontal. So if your page has that kind of length or width, then you can draw it. It is better to be drawn in a single page because you have to have the cam profile which needs to be drawn after this. So if you take 1 degree as 1 mm, you will require 36 mm line in the horizontal direction like this. A 36 mm line would be required. And if you don't have that, you scale it accordingly as either 2 degrees equal to 1 mm. So you can contain the 36 degree, 360 degree in a 180 mm line. And if you do the scaling accordingly, you can contain, but it is generally mentioned not to scale it too small or too large. So again, if I'm now taking 2 degrees 1 mm, that will be convenient for everyone. So you will get 360 degrees equal to 180 mm or 18 centimeter. Similarly, vertical scale you can take, since it is only 30 mm given, you can take 1 mm is equal to 1 mm. So you will get 30 mm, which is the maximum lift, will be equal to 30 mm or 3 centimeters. Or if you want to draw it a little larger, which I am going to do now, I am taking it as 0.5 mm as 1 mm. So I can draw a larger diagram, which is easier to explain. And so 30 mm lift will be mentioned as 6 centimeter. So these are the two scales you have to mention in the beginning. So let's erase this one. Okay. So let's start drawing the displacement diagram for the uniform velocity motion. So as I said, you have to have a horizontal line, and that line needs to be according to your horizontal scale. I am taking 2 degrees 1 mm, so total I need is 180 mm or 18 centimeter. So take a ruler in centimeter, place it. So this is our beginning point. So 15 mm, and if you move it to another 3 mm, you will get 18 mm. So this is our 18 mm. Now we want to divide this horizontal line into outstroke, dwell, return stroke, and the last dwell. So outstroke is 120 degree. So 120 degree means 6 mm according to my scale, or 6 centimeter according to my scale, because 2 degree is equal to 1 mm. So I'm taking 6 centimeter to mark the outstroke. If you place the scale correctly, it will come as 6 mm. Now, next dwell comes at 60 degree. You can see next dwell is 60 degree. So 60 degree dwell, this one can be represented as another horizontal length. So 2 degrees equal to 1 mm. So 60 degree will be 3 centimeters or 30 mm. Then another return stroke that is equivalent to 120 degree. So that 120 again can be represented by 6 centimeters. So that will be approximately here. So let's erase that one and draw it correctly. So 6 centimeter. Yeah. So 6 centimeter will be that point, this one. And the last one will be the again 60 degree, that will be 180. So that will be our line. So let's erase everything else to avoid confusion. That will be the line, and the vertical scale is 30 mm maximum lift. So maximum 30 mm can be drawn as 3 centimeter. I am taking it as a little larger scale so as to magnify and show you clearly how to draw it. So from here, if I take a length of 6 mm, yeah, so that will be 6 mm. So now you can make the triangle by drawing a horizontal line and cutting across with the other edge of the triangle. So you can do it by measuring or by using a scale by carefully drawing a perfect horizontal line and a perfect vertical line. So now that is our rectangle. Now you can divide that rectangle into outstroke section that we marked earlier, 120 degree, dwell section 60 degree, return stroke again 120 degree, and the last dwell as 60 again. So let's mark it. So this is 120 degree, 60 degree, 60 degree, and also the vertical direction 30 mm. You should write the original dimensions. Now to draw the velocity diagram, sorry, to draw the displacement diagram, we need to divide this outstroke and return stroke into equal number of parts. It is always better to do it in even numbers, because in uniform velocity method that doesn't matter whether you divide it in even numbers or odd numbers. But when you do simple harmonic motion, cycloidal motion, or in uniform acceleration deceleration motion, then that even number should be the number you should choose. So let's divide it in even numbers. So it is 120 degree. It is easy to divide in 6 parts. You can take 220 degree as the equal number. So we have taken 2 degree as 1 mm. So if you want to divide 120 degree, that is 6 mm into 6 equal parts, you can just take 1 mm in the scale. So let's take 1 mm. So I'm dividing it into 6 pieces. 1, 3, 4, 5. Do the same thing in the return stroke also. Dwell, we don't have to divide anything. Only return and outstroke we want to divide. It is better to do it in the equal number of parts on both return and dwell. Okay. So now you construct the lines again. You can use a smaller bold lines to do that if you have. Otherwise, you can do it with the solid lines. Just constructing it. So that will be the divisions. Now, since this triangle will be same up to here, it is same for all the methods, whether it is uh, uniform motion, simple harmonic motion, or cycloidal motion. This construction of triangle and division is same for every kind of follower motion. So you should, I will explain this time, and next time I will just copy this diagram. So for uniform acceleration, deceleration, and simple harmonic motion and cycloidal motion, we have to draw circle, semicircle, like those things. But for velocity, uniform velocity, there is nothing to do. It is the most easiest method to draw the displacement diagram. Just take a scale, place it to the one end of the return stroke corner to the other end of the return stroke corner, and just draw a line as a diagonal like this. So let me use a different color pen so it will be more visible and attractive for you. Why is it not coming? Yeah. So just draw this as the diagonal. This is the most easiest displacement diagram you can draw. And for dwell, you just draw a horizontal line across that. Then again a diagonal in the return section. And since last dwell is mentioned there, you should draw a horizontal line that. So this is your displacement diagram for the follower with uniform velocity motion. And we need this length, so name it uniformly. So you name horizontally as 0, 1, 2. Let me use another color. So 0, 1, 2, 3, 4, 5, 6. And in the return stroke, you name with the same notation but with a dash. 1 dash, 2 dash, 3 dash, 4 dash, 5 dash, and 6 dash. And in the slanted side, you name it as A, B, C, D, E, F, G, and you continue with that H, I, J, K, L, M, N, and last one will be O. So this is our displacement diagram for the uniform velocity motion. And what we require for drawing cam profile is the length represented by this one. This one, I will just mark it with a blue line. That will be easy. What we require is this length of this line because this is what we need to draw the cam profile. So this is just the first step of cam profile. We need the length of this blue lines that I am marking, which is cutting the displacement diagram from the horizontal. This length has to be traced onto the circle to draw the cam profile. So I am just mentioning that also. So I will be using the same figures for while we draw the cam profile in the later sessions. So those lengths are required, the blue lengths. So this is the how you draw the velocity diagram, sorry, displacement diagram for a uniform velocity motion. I hope it is clear, very easy. So please do it carefully.